Hi everybody, Patrick here from Engineering Shock Electronics, www.engineeringshock.com, and this is the Arduino Epoch Learning Center, project number 27, data logging. Now lots of stuff going on here. We're going to be using the SD card slot, the real-time clock, which we've used before. If you haven't already done project 24, highly suggest you do it. We're going to use our motion sensor. Our state dip switch is connected, but we're not going to use it, but I'll talk about it because it's part of the code. It's basically a rehash of Project 24. I'll get to that in a minute. And we're using the green and red LEDs. Now, the idea behind this project is that we put in an SD card. You'll need your own SD card. I highly suggest these Samsung SD cards. This is an 8 gig SD card. You can get an adapter, a USB adapter on Amazon or eBay for next to nothing. And what I'm going to do is turn power off. And I'll plug in my SD card. Now before you put in your SD card, what you need to do is open up the SD card on your computer, and you need to create a text file. So just right click in the window, new text file, and name the text file, well, whatever you want if you're willing to change the code around. But if you want to work with the code that I'm providing, create a text file called sdtest.txt. So sdtest.txt. And it'll be a blank text document, and that's what the code is going to write to. So I'm going to power it on, and I want to show you from the top side of the board as well from the serial monitor, because the serial monitor is going to be doing a whole bunch of processing for us, telling us where the code is at. If your real-time clock isn't connected properly, or the SD card is removed or not connected properly via the SPI communication lines, the project will freeze. You don't want that to happen, so I'll do the demonstration now, and we'll do the connections after the fact. So I power on. What happens is the code says waiting 60 seconds for the PIR motion sensor to become stable. And if you remember an earlier project when we talked about the motion sensor originally, when you power it up, it becomes funky, and you want to give it about a minute to say, "Hello world, I'm here. Let me just get used to you before I become stable." Now after it becomes stable, after 60 seconds, the project starts scanning, and when it detects movement, it will write the current time and temperature and date from the real-time clock, which has an internal temperature sensor, to the SD card, and then while that's happening, the red LED will turn on for a short period of time. Once it's done writing, the green LED will turn on for a minimum of 10 seconds, at which point you can power off if you want. The reason I put those in there is because you don't want to unplug while it's writing to the SD card, and I've added in a 10-second delay after it's done writing so that you have the time to power down if you want. And after that 10 seconds is up, there's actually a while loop that says do nothing if the output of the PIR sensor is still high. So it's a minimum of 10 seconds. In any case, that's what happens from a board level, the two LEDs. That's all you're going to see of the two LEDs. But we're not going to see what's really going on in the project without looking at the serial monitor. So first things first, let's look at the serial monitor, and I'll walk you through what's happening in the code. So we'll go to Tools, Serial Monitor, and initializing SD card initialization done. If the card wasn't connected properly, it would say failed, and it would freeze. So it says waiting 60 seconds for the PIR sensor to become stable. So I'm actually leaning on the ground right now. The motion sensor can't see me, and so after 60 seconds it'll say that it's become stable, and then it will wait for a trigger, at which point I'll put my arm up and it will write the date and time and the temperature to the SD card, assuming that everything is connected properly. And so we use the SPI communication lines, so SPI clock, MOSI, MISO. MOSI is MOSI, which is master out, slave in, and MISO is master in, slave out. And the slave in this case is the SD card. We're also using the I2C lines to communicate with the real-time clock. And that's covered in Project 24. So we're using two different communications protocols here, SPI and I2C. And we'll probably talk about those in detail down the road a bit. Again, I'm going to create so many videos. So PIR stable. So now it's just going to wait. It's just going to say PIR stable. Nothing's going to happen. As soon as I move, the red LED is going to go off until it's done writing. Then the green LED is going to turn on after it's done for 10 seconds, in which case I can remove power, which is what I'll do. If I continue to keep the program on, it will just keep logging like that. As soon as the green LED turns off, it'll wait for motion to be detected again. So I'll actually detect it twice, and we should see two different values written on our SD card. Now, before I keep going, in Project 24 we use the dip switch, 4-channel dip switch. We use channel A, and if we set that to on, then the output of that dip switch is high, which means that we'll be implementing an if statement. If that line is high, write a new time to the real-time clock on power up, which means we can change the current time if the time that's on the real-time clock isn't accurate. Again, that is Project 24. Go back to it. It's kind of a prerequisite. In any case, so I'm going to put my arm up. Writing to SD text, the red LED is on. Done. Red LED is off, green LED is on. And after 10 seconds, what will happen is it will tell me that it's done, and it's going to wait for movement again. Awaiting next movement trigger, or movement trigger. So now it's just going to keep doing that over and over and over again. We'll move. Writing to SD test.text. Done. The green LED is on. I'll remove power. Now I can show you, I can do all that again and wait 60 seconds. I've removed power. I can wait another 60 seconds and show you, but basically, as soon as it starts writing, it's going to write for about 2.5 seconds. The red LED will be on. Don't remove power. As soon as green LED turns on for a minimum of 10 seconds, then you can remove power. And it'll just keep writing and writing to the SD card. So I'm going to keep this. I'm going to keep my camera on. Hopefully it doesn't go out of focus. I'm going to remove the SD card, and I'm going to put it into my adapter. I'm going to remove the Arduino connection to the back of my computer because I don't have a hub. And I've got my SD card connected to the computer now. So I'm going to go down to drive F, which is my drive currently for the SD card. I'm going to choose SD test.text, and there we go. We have, the date is 2020, month October, the 20th day of October, which is accurate. It is a Tuesday. The time is a little bit off because I haven't reset it. It says that it is 1:51 p.m. and currently it's actually 2:20. So I need to. This is because I've rewritten to the RTC a long while ago, and it just needs to be updated. So you can update that. That's in the code. There are a few challenges. There's one even actually hidden in the code, which I hope you'll look for, because part of how you're going to learn is not just by copying and pasting. It's by experimenting with the code. And again, if you mess up a code and you can't fix it, just re-download it. It's at the project page. So, what am I missing here? I feel like I'm missing something paramount here. If you're going to use an SD card, again, those Samsung ones are great. You have to if you don't have the SD.h library, you need to download it from GitHub. But I think that Arduino comes with it as a standard. But GitHub is a great place to find libraries for fun parts. So let's talk about how we put this thing together. Now, all of the connections are written in detail in the code, but maybe I'll just work backwards. If you want to work along with me, that's fine, just really working backwards. First, the LEDs. We've got the red LED, G LED, connected to GPIO pin 5 on chip A. We've got the red LED, RLED, the RLED pin connected to GPIO 6. So, GPIO 8 is connected to state dip switch channel A, which is turned off. And again, in the code, if you turn it on, you can update the RTC, the real-time clock, with the current time. You just need to enter in the current time into the code. Turn it on, press reset, and it'll update the new time. And then you just turn it off again. It's currently in the off position, which means it sees 0 volts, so it's low. So I'm going to remove those 3 connections that we've talked about. Next, the PIR motion sensor. There's 2 PIR pins you can connect to right in here. It doesn't matter which one, they're both connected together, and that is connected to GPIO pin 3, right here. Let's remove that. GPIO pin 3 to one of the 2 PIR pins. GPIO 4 is on chip A is connected to SD_CS for SD chip select. So the SPI communications protocol requires not only the clock input and output to master to slave, but it also requires chip select. So basically we're saying, hey, I'm talking to you, not you or you. The SPI communications protocol allows for you to talk to so many things, and it determines which one it's talking to by a chip select line, which is pulled low when it's talking to a certain chip. So GPIO pin 4 to SD_CS chip select. We've got the A5 pin on chip A, analog pin 5, which is also the SCL line, which is I2C clock, and that's connected to the SCL RTC line right here, just labeled SCL. So SCL is connected to A5, removed. SDA for I2C data is connected to the A4 line, and we will remove that. A4 is over here next to A5. So now we've got the three remaining SPI lines. Excuse me. So GPIO pin 11 is connected to SD MOSI for master out, slave in. So pin 11 has the master chip talking to the slave. We'll remove that. GPIO pin 12 in yellow is connected to SD MISO, which is master in, slave out. So that's the slave talking to the master. Lastly, GPIO pin 13, the last SPI communications line, is connected to SD S-Clock, SCLK, and that is our clock line. So, punk, done. It's actually a really fun project. This really gets you into the idea of data logging. We can log. I really want to do a lot of data logging over the next 6 months with this board, because there's so many different ways to log data. You want so this project, you can modify it so it's a bit more secretive. You don't have to have the LEDs on if you don't want to, but you don't want to unplug it when it's potentially writing to the SD card. You won't ruin the SD card, I don't think. I'm 99% sure, but still, you don't want to be writing to something and then remove power. You can make it more secretive, so it's just kind of lying dormant, but it's also detecting movement and showing you. You can even write it so it says movement triggered at the date. I didn't do that in the code. You can do that. Check out the challenges. Super easy. And when you're done, because we're not using the PIR motion sensor, plunk, get rid of it. We don't need things plugged into the board consuming power that aren't being used. Like the RFID reader, which we'll be using very, very soon, that's not consuming any power because we have all the quick connect dip switches off. So that's that. Super simple to hook up. The code is a bit complicated, but again, if you've been following the projects up until this point, it should be relatively easy peasy. Some of the more complicated lines of code that are a bit more foreign, they are library specific. So some libraries are written with lines of code that are a bit harder to decipher, but if you follow my line of thinking in the comments for all of the code, it should come pretty easy. And again, you have to experiment with it. Write your own pieces of code with the RTC, and with the SD card reader. Just write to it. Practice writing to it. Practice writing different values to the real-time clock. Really wonderful pieces of technology, and they're really not difficult to use. And of course, we have our battery backup. Without this battery backup, the RTC will not work, and this just keeps the time. When this battery dies, and it has usually a long life, when the battery dies, you just replace it and reprogram the time, because when you remove this power supply, it will stop remembering the current time. So what's left for the blocks? We have the vibration sensor and the RFID reader, the NRF24L01 Plus, and the Bluetooth reader. Now, I can't do a proper project with the NRF24L01 Plus or the vibration sensor until the new boards come in. I'm expecting them in Monday of next week, hopefully Friday. When that happens, I'll do projects for this and the vibration sensor. The reason we can't do the vibration sensor is because I accidentally left a pin out to connect to on the previous version. This is the prototype version, but the first 3 units will be coming in, and then once I've quality checked those, we'll have the remaining 197 from the Kickstarter manufactured. But yeah, I don't know what I'll do next. I'll probably do the RFID reader next, and then the Bluetooth module. And for the Bluetooth module, that's going to require a heck of a lesson, and I'm not prepared to do that at this time. I'm actually going to do a bit of a cheat. I did a Kickstarter with the HC06 Bluetooth reader before, which plugs in right here, and I used the RoboRemo app, which allows for you to do a lot of really neat things. There's a lot of great tutorials online on how to use it, and what I did was I created a UI within the app, and it doesn't, trust me, it sounds difficult, it's not, and I created that UI user interface to work with my then Kickstarter campaign, and what that does is it turned on and off 4 relays. And so I can use that exact same UI, which you can import into your phone. Now, it was designed for Samsung. I'm not sure if it works for Apple, but the Samsung version, you just have to take the file that I'll provide, upload it to the right spot in your phone, and instructions will be provided. plug in your HC06 and follow along, and we'll just use one relay, and we'll use the 3 LEDs as the remaining relays. Basically, as just indicators that they would be relays on and off. And it'll be a bit of a lesson regardless, but down the road what I want to do is I want to create a UI as part of a lesson. But the great thing about the internet, even Instructables.com, there's tons of different ways to use the HC06 Bluetooth reader. This is just a simple one, and I'll get to that relatively soon. Then we're getting into some of the harder blocks, and so more complicated blocks anyway, so they take a little bit more time to make videos like this. Anyway, I'm rambling. Thanks for watching, everyone. I hope you have a great day. I hope you've enjoyed the video. If you haven't already, check out the Kickstarter campaign. The Kickstarter's done, but you can still view the project page located within the Kickstarter campaign for a short period of time until it becomes password protected for those who pledge towards the Kickstarter. Thanks for watching. Have a wonderful day, guys.